So in this lesson, we're going to take the concept of Lewis dot structures, and we're going to actually see the shape that is formed for these molecular compounds. So right here, if you look, I'm just going to go through this and explain it. If you have two electron groups, so that means either bonding electrons, so shared electrons, or lone electrons, if you've got two groups, then the shape is going to be linear. Okay? And so if you look at this example, if it's linear, then the angle, the bond angle, is going to be 180 degrees. Okay? If you have three electron groups, just three, okay, then it's going to be, the electron group geometry is going to be trigonal planar. Okay? Now notice that the shape is also trigonal planar, which begs the question, when would it not be the same, the electron group geometry and the shape? Let's look at an example. The next one, you've got three electron groups. It's trigonal planar for the electron geometry, but notice you've got two bonding and one lone. If you look at SO2, you've got two bonding, so you've got two atoms that are sharing electrons, and then what isn't represented is you've actually got two lone electrons on top. So if you've got two bonding, one lone, then the shape is going to be bent. So while the electron geometry is still trigonal planar because you've got three electron groups, two bonding, one lone, the shape is going to be bent. For the next one, if you've got four electron groups, the electron group geometry is going to be tetrahedral. If all four of those are bonding, then the shape is also going to be tetrahedral. So that's an example like for CH4. If you've got four electron groups, but three are bonding and one is lone, like for example in NH3, you can see you've got three atoms that are sharing electrons, and then there's going to be one lone group on top of that nitrogen there. So three bonding, one lone, then the shape is going to be different from the electron group geometry. The shape is going to be trigonal pyramidal because it looks like a pyramid. Then if you've got four electron groups, but two of them are bonding and two of them are lone, then your shape is going to be bent, just like water. Because for water, you've got two pairs of shared electrons, two bonds, and then you got two pairs of lone electrons. So those are the only shapes that for this class you are going to be responsible for. So let's try an example. So here I've given you PBr3. Okay? I've got to first count my total number of valence electrons. So I've got 5 from phosphorus, 7 from bromine, but they're 3 bromines, so that'd be a total of 26 valence electrons. Okay? Now I'm going to share electrons. So I'm going to draw lines in between these guys. And then I'm going to make sure all of my atoms have 8 valence electrons. So I'm going to start with my outer elements. So bromine needs 8. Right now each bromine only has 2, so I've got to add my lone pairs. Notice I drew a line instead of the 2 dots. If you want to draw a line instead of 2 dots, that's fine. It just saves a little bit of time. That's how I draw mine. Okay? And then phosphorus right now has 6. It needs 8, so I'm going to add 2 there. And so I'm done there. Now if you notice, I've got 1, 2, 3 bonding pairs, because I've got 3 bonds there, and then I've got 1 lone pair. So I've got a total of 4 electron groups, which means the shape of the electron group geometry is going to be tetrahedral. But notice I've got 3 bonding and 1 lone. So the shape of this molecule is not going to be tetrahedral. What you actually are going to see is trigonal pyramidal. And then the last thing is the angle. So if you look back at that table, for a tetrahedral, the angle, the bond angles, are going to be about 109. Okay, so that's all there is to it. The next thing that we need to add on to this is electronegativity and polarity. Remember, as you move across the periodic table, electronegativity increases the attraction for electrons. That's what electronegativity is. As you move across, it increases. As you move down, it decreases. Okay, so this is going to be important. We're going to look at why in just one second. So, when we are sharing electrons, if electrons are shared equally because they are being pulled equally by atoms, then the bond is going to be nonpolar. So if you look, for example, at hydrogens, those share the electrons equally because they have the same electronegativity. if two atoms that are sharing electrons have different electronegativity, so for example, hydrogen versus chlorine, chlorine has a higher electronegativity than hydrogen, and so chlorine's actually going to be hogging those electrons. So the way that we represent that hogging, let's look at an example for me to show you. So if I were to draw this HCl, okay, what I would do to show that chlorine is hogging those electrons is I'm going to draw an arrow. I'm going to show a vector. And that shows that those electrons are being pulled more towards chlorine than towards hydrogen. And so we are going to use this in order to be able to determine if a molecule is polar or nonpolar. Okay, so let's look at an example. So here, let's look at the nonpolar. If you notice for CO2, oxygen is more electronegative than carbon. So you've got one arrow going towards one of the oxygens, another arrow going towards the other oxygen. Notice that those, what we call those dipoles, those arrows cancel each other out. That means that the molecule is nonpolar. If you look at CCl4, okay, you've got chlorines pulling those electrons, but notice you've got an up and then three downs. If you imagine that in a tug of war, those vectors, those dipoles, would cancel each other out. So it's going to be a nonpolar molecule. If you look at HCl, however, notice since Cl is more electronegative, the arrow is going to be pulling towards it. It's going to be pulling the electrons towards it. But notice there's nothing counteracting that. So since the dipoles do not cancel out, that means that the molecule is polar. For NH3, nitrogen is more electronegative, so the arrows are going to be going towards nitrogen. Notice that there's nothing, if you imagine like a tug or push of war, right? Those arrows are not going to be canceled out. That dot's going to move, which means that the dipoles do not cancel, which means that NH3 is also polar. And we'll talk about the significance of polar and nonpolar in the next lesson. Right now, I just need you to be able to draw these and determine if the molecule is polar or nonpolar. So let's look at this example. I'm going to draw my Lewis dot structure. Okay, so I've got HF, hydrofluoric acid. I'm going to draw the Lewis structure. There it is. Fluorine is more electronegative than hydrogen, so I'm going to have my vector facing towards fluorine because fluorine is hogging those electrons. Notice nothing cancels out that dipole. So as a result, HF is going to be a polar molecule, and that's it.